right, let's talk about some applications for common and natural logs here. We are going to solve a couple problems with these guys. Now, you could solve them with common logs. I think I'm going to do all of my change of base with natural log if I come across that. So, find the percent of women who had a baby and returned to work in 1995 using the previously mentioned equation. Okay, so this is a classic textbook move. They only have so many pages, right, that they can produce. And so what they'll do sometimes is reference an equation that was previously made. We actually never even looked at this equation. This one is the percentage right here. This is the percentage of women who had a baby last year. It's actually back on page 14. So let's copy paste that back real fast. 38.83 f of x. Whoa, zoom in here. So f of x is equal to 38.83 plus 4.208 log 2 of x. 4.208 log 2 of x. Okay, again, classic textbook move, making you do the work, right? So now we need to find the percentage of women who had a baby and returned to work in 1995. So how does this equation even work? Let's go back. The percentage of women who came back and returned to work is the function, and for year X since 1980. So this is since 1980. So X is since 1980. 1995 is 15 years since 1980, and so that is what I will plug into the function. So we are looking for 15, f of 15, okay? Not f of 1995, right? We don't automatically assume that it's a scale of 1, right? We don't automatically assume it's starting at 1. Most of the time with the real world, we don't want to start at 1 because then we have awkward positions where something like this, right? We have 1995, and we don't want to have to plug in 1995 to a function. So let's go ahead and plug in 15 to that function and see what to do. This should be pretty nice because it's all on one side. Doesn't look like there's going to be a lot of solving here. Log 2 of 15. The only thing I might worry about is this guy right here. I don't think has a button in the calculator, so I'm going to have to do a change of base formula here. I might just convert it here. I might do it on the fly as I'm punching numbers in, but I think for the notes, we should probably convert this to ln of 15 over ln of 2. And we'll just say, like, okay, we changed that. This is equal to, we'll go over to the calculator now. Calculator's smart enough to handle the whole thing at one time. Plus 4.208 ln of 15 divided by, oops. Now that actually would have been the same, but I do want to stick to what my notes are saying. ln of 2, so 55.27% of women in 1995 went back to work right after that. That's kind of cool. I would imagine the number is a little higher right now. Lovely. All right, another example. The wetlands are classified as bogs, fens, marshes, and swamps on a basis of the pH values. A pH value between 6 and 7.5, such as that of Summerby Swamp in Michigan, Michigan's Hiawatha National Forest, indicate that the wetland is a rich fen, while the pH between 4 and 6 is the wetland is a poor fen, and if the pH falls below 4, it is called a bog. Suppose that a hydronium ion concentration of a sample of water from the wetland is 6.3 times 10 to the negative third. How would you classify this wetland if the pH calculation is calculated with the function p of h is negative log H3O plus content? Whew, that was a lot of words. Okay, so let's back up here. What's going on? We've got this formula that is calculating the pH of a swamp. Apparently, if you have a swamp that's under 4, it's a bog. Between 4 and 6, it's a poor fen, and above 6 to 7.5 is a rich fen, and we don't know what's going on after 7.5. So we have this concentration of ions, and it looks like, so that is H3O plus is 6.3 times 10 to the negative third, scientific notation, okay? And then we plug that in, since we've got 10 to the negative third, log makes sense, right? Scientific and log going together. Looks like we're going to be plugging that in and calculating it. So let's go ahead and do that. I don't know about plugging in a scientific formula, so since it's not too small, we could do scientific convert back, 0.1263. Just in case you forgot how to do that, here's the current decimal place. We go back 1, 2, 3, same number. So we get 0.0063 is what we will plug into the equation. Negative log 0.0063. Don't worry about the brackets. I know that a lot of times we use brackets to distinguish between parentheses and brackets we do for a domain and range, right? But in this case, this is just science using a bracket to be very formalized about it. So we're just going to go ahead and plug that calculation in. Now remember, there isn't such thing as a negative log, so this is really -1 times log. And we have a 2.2 pH, which would classify this as a bog. This is not a fen. This is gross, disgustingness. All right. What about a pH concentration of 3.16 times 10 to the negative second? What if it was that concentration? All right, so we've got 7 back now, 0.1, 2, 3, 4, 5, 6, and then the 3. We're going to plug that into negative log. And we get 1, 2, 3, 4, 5, 6, 7, 3, 1, 6, 7.5. Interesting. So it looks like the less of this ion that you have in your wetland, the better the bog. So this would be a rich fen. This is even the highest, the almost beyond the rich fen. It's actually almost above it. But 7.5, we'll call that 7.5. It's right at the edge of rich fen. Nice. All right, third problem here, last one of this video. The number of years R of n of R, since two independent evolving languages split off from a common ancestral language is approximated by n of R is equal to -5,000 lnr, where R is the percentage of words in decimal form from the ancestral language common to both languages now. Well, that's kind of cool. Find the number of years to the nearest 100 years since the split for each percent of the common words. Okay, so it looks like R is the percent of words they have in common, and n of R is the number of years that has been since the split. Okay, so let's see. If they have 85% in common, then that's going to be n of, whoops, my n's always look awkward, n of 85. But I don't want to put in 85, right, because this is a percent. It would be, it even says right here, in decimal form, and an 85% would be 0.85. So all those little things you see are coming back. Like, how do you deal with scientific notation? How do you deal with percents, right? Those are always consistent whenever we're dealing with application problems. These bigger tools, ln, we can look those up. But knowing how to do a percent, that's like a critical thing. You got to be able to do a percent real fast. So 0.85 minus 5,000 ln of 0.85. All right, so that looks like this entire side is actually just numbers. I can jump over to the calculator. Negative ln 5,000. Nope, just kidding. 5,000 ln of 0.85. Looks like it has been 812.6 years to the nearest year, hundreds to the near, hold on, years. But it says to the nearest 100 years, so we would say 800 years. 800 years since, whoops, pardon me, since that split, right? Because this isn't a very accurate equation. We're talking about languages here, right? Who can pinpoint a language to a 0.6 of a year that it changed, right? So we're saying 800 years are about the split. All right, let's do it again. We got another percent here. We have n of 0.35 negative 5,000 ln of 0.35 here. Jump back over to the calculator, just change that to a 3. 5,000, which makes sense. If you have less in common, it's probably been longer, right? It's probably been a longer time. Again, it's to the nearest 100, so I could just round this off to 5,000 years. Don't even need to worry about rounding that decimal place. Sweet. Last one, find the percent if they split after 10,000 years. So this one's probably not a plugin, right? They want us to find the percent now. The percents are the R. They gave us an N. So 10,000 equals negative 5,000 ln of r. We actually got to solve this one. Unfortunately, the variable is within the formula, so we're going to have to move things around. So negative 5,000 to the other side. We get negative 2 is equal to ln of r. E to the negative 2 is equal to r, or about, let's see, what is e to the negative 2? 0.135%. Oh, right, 0.135, sorry. It's so yeah, I even got caught up. It's as a percent, so we're looking at 13.5% in common. Not a lot after 10,000 years. All right, that's just 3 of the many examples, kind of all over the place, science, language, medical, that you can find some logarithmic equations. Notice it's not too bad, though. Now that we have those natural and common log functions in our calculator, we can just use our reasoning skills and follow a lot of these. The last video we'll talk about is a couple more log examples, kind of how to solve some more of those equations for variables, kind of formulas, and I will see you there.